Hey, you know how the internet is just, well, completely full of pictures and videos of cats?
Oh, yeah.
Especially crammed into the most ridiculously tiny places. Sinks, boxes that look way too small, even like delicate glass bowls sometime.
Mm-hmm. It's classic internet cat stuff.
It's endlessly amusing, right? And it really makes you wonder, when you see a cat just sort of melt into a space, are they actually liquid?
That question, it might sound a bit silly at first,
Yeah.
but it actually takes us into a really fascinating area of science. Physics, actually.
Physics for cats in boxes.
Yeah, specifically a field called rheology.
Rheology.
It's the study of how materials deform and flow. Think of it as, the science behind why honey pours slowly, but water pours fast.
Yeah.
Or why some things stretch and others snap.
Rheology. Okay, let's unpack that. So you're saying the way a cat can just seem to, ooze into a space the size of a bread box isn't just some cute quirk.
Uh-huh.
It's something physics might actually explain.
Exactly. And it's not just like bit of fun online chatter. Back in 2017, there was this rheology researcher, Marc-Antoine Fardin.
Okay.
He actually won an Ig Nobel Prize in physics for his work specifically on the rheology of cats.
An Ig Nobel. Aren't those the ones for science that makes you laugh, then think?
That's them. They celebrate research that seems funny or unusual, but actually has some deeper scientific point or sparks curiosity.
An Ig Nobel for cat fluidity. That's brilliant. Okay, so for this deep dive, our mission really is to explore this whole question. Are cats liquid?
Right.
And we'll be looking at Fardin's work, that physics perspective, but we're also going to dig into a really interesting biological study that looks at it differently.
That's right. We've got this paper from iScience. It's titled, Cats Are Almost Liquid. Cats selectively rely on body size awareness when negotiating short openings. It's by Péter Pongrácz.
Almost liquid. Okay.
And this study gives us a look at how cats themselves seem to perceive their own bodies and interact with, physical limits, how they judge spaces.
So we've got two angles. The physics angle, cats is liquid. And then the biological angle, what the cat itself seems to know about its size when deciding if it can squeeze through something.
Exactly. Two different ways to tackle the same slippery question.
Sounds like we might uncover some pretty surprising stuff for everyone listening.
I hope so. So maybe let's start with that rheological view.
Yep.
From a physics standpoint, what actually defines a liquid?
Well, the classic definition, and Fardin brings this up too, it's pretty straightforward, right? A liquid is something that changes its shape to fit whatever container you put it in.
Uh-huh.
And if you've ever watched a cat settle into, say, a bathroom sink.
Oh, yeah.
You can definitely see the resemblance, give them a little time, and they really do seem to just mold themselves right into the curves.
And that phrase you use, give them a little time, that's absolutely crucial here.
Right.
In rheology, this connects to a concept called relaxation time.
Relaxation time.
Think of it as the characteristic time it takes for a material, whatever it is, to adjust its shape, to rearrange itself under stress or confinement.
Okay.
And whether we perceive something as acting like a liquid or acting like a solid really depends on how long we're observing it compared to that relaxation time.
Okay, so a cat getting comfy in that sink has its own relaxation time, the time it takes its body to fully sort of conform to the sink's shape.
Exactly.
And if we watch it for longer than that time, then to us it looks like it's behaving like a liquid.
Precisely. So Fardin's playful point is that cats can be considered liquid. It just depends on the time scale. If their relaxation time is shorter than how long you watch them settle, then yep, liquid cat.
Huh. So the state isn't fixed. It depends on time.
Right, and that relaxation time itself probably isn't fixed either. It likely changes depending on various factors.
Like what sort of things? Would like a young, super bendy kitten have a faster relaxation time than maybe an older, stiffer cat trying to fit into the same box?
That's a really good question. And Fardin actually draws a parallel here to a rheological property called thixotropy.
Thixotropy.
Yeah, it describes materials that become less viscous, more fluid, essentially when you shake them or stir them or apply stress over time. Think about some paints or even ketchup. You shake it, it flows easier.
Right. Okay.
So maybe, just maybe, a younger, more active cat's cat material becomes more fluid-like with movement, allowing it to conform faster. It's an analogy, but it kind of fits, doesn't it?
It does, actually. What about the container itself? Does that matter? Like, is it easier for a cat to liquefy into a smooth sink versus, a lumpy cardboard box?
Absolutely. That could relate to what rheologists call wetting problems.
Wetting.
Like water.
Sort of. It's about how well a liquid spreads out on or adheres to a solid surface. So a cat might mold more readily into a smooth, curved surface where its body can make good contact all around,
Uh-huh.
compared to a rough box with sharp angles where maybe doesn't wet the surface as well, metaphorically speaking. That makes a lot of sense. He also mentioned stress levels, which sounds funny in this context. How could a cat's mood affect its flowability?
Yeah, this is where the analogies get really fun and maybe a bit stretched, but still interesting. Fardin connects it to concepts like shear thickening and shear thinning.
Okay.
So some materials, when you apply stress like squeezing or stirring, a shearing force, they get thicker, more resistant to flow. That's shear thickening, like cornstarch and water.
Oh, yeah, oobleck.
Exactly. Others get thinner, they flow more easily under stress. That's shear thinning, like paint. So translating that very loosely to a cat's emotional state.
Right.
You could imagine, perhaps, that a stressed, tense cat might resist conforming. It might metaphorically thicken, whereas a relaxed, happy cat might just melt into place, behaving in a more shear thinning way.
Okay, I can kind of see that. A chilled out cat just sort of collapses into a comfy spot.
Right. It's playful, but it connects to real physical concepts.
So we've got age, maybe activity, the container shape, even stress, all possibly changing how fast a cat seems to become liquid. How do scientists, quantify this, put a number on it?
Well, this is where a key concept in rheology comes in, the Deborah number.
The Deborah number, okay.
It's named after the prophetess Deborah from the Bible, who sang that the mountains flowed before the Lord.
Casting long timescales to flow.
Exactly. The Deborah number is basically a ratio. It compares the material's intrinsic relaxation time, how long it needs to adapt, to the experimental time, which is how long you're actually observing the process.
Okay, so it's relaxation time divided by observation time. What does the result tell us?
It's pretty simple. If the Deborah number is high, much greater than 1, it means the relaxation time is longer than your observation time.
Right.
So during the time you're watching, the material doesn't really have enough time to flow or adapt. It behaves more like a solid. Think about flicking silly putty quickly, it snaps like a solid. Or that water balloon popping for a split second, it holds its shape. High Deborah number.
Got it. And if the Deborah number is low, less than 1,
Then the relaxation time is shorter than your observation time. The material has enough time to adapt and flow while you're watching, so it behaves more like a liquid.
like the mountains flowing over geological time.
Exactly. Or like that cat settling into the sink over, say, a minute. If its relaxation time is maybe 10 seconds, then over that minute, its Deborah number is low, 1060, and it appears liquid-like to you.
Okay. So when we see those pictures of cats perfectly molded into tiny spaces, assuming they've been there a little while, their Deborah number in that situation would be low. They're acting like a liquid on that timescale.
That's the idea Fardin was exploring. He also playfully mentions other numbers rheologists use, like the Reynolds number, which predicts turbulent versus smooth flow.
Like, would the cat pour smoothly or splash into the box?
Huh, kinda. And the Weissenberg number, which relates to elastic effects in flowing materials. It's mostly for fun in the cat context, but it highlights how rheology uses these dimensionless numbers to describe complex behaviors.
It definitely gives you a whole new lens for watching cat videos. But okay, let's shift gears. That's the physics perspective. What about the biology? This iScience paper by Pongrácz, they actually tested cats, right? Watched how they dealt with openings.
Yes, exactly. This study takes a totally different approach. It's not about passive molding, it's about active decision-making. Do cats know if they can fit?
Right. So how did they test that? What was the setup?
They worked with 30 regular pet cats, tested right in their own homes, which is nice and natural.
Uh-huh.
They basically set up these cardboard panels that the cats were encouraged to walk through. The panels had openings, and the key thing is, they systematically changed the size of these openings.
Okay. How did they change them?
They did it in 2 distinct ways. In one set of trials, the openings stayed the same height, but got progressively narrower.
Okay. Tall and skinny getting skinnier.
Right. In the other set, the openings stayed the same width, but got progressively shorter.
Ah, wide but getting lower and lower, like ducking under something.
Exactly.
Yeah.
A really clever way to see if cats judge horizontal squeezing differently from vertical squashing.
Totally. So what happened? Let's take the first case, the tall openings that just got narrower. How did the cats react as the gap got tighter?
Well, this was really interesting. The researchers found that, generally speaking, the cats approached and actually went through even the narrowest of these tall openings.
Yeah.
Without significant hesitation beforehand. They just sort of went for it. A couple of cats did decide to jump over when it got really skinny, but mostly they seemed willing to try squeezing first.
Wow. So they weren't standing back and thinking, that looks too tight. They just tried.
It seems that way. The study suggests they might rely more on, like, trial and error for those narrow vertical gaps, or maybe other cues right at the entrance.
Like what? Their whiskers, maybe? Feeling the edges as they go in?
Exactly. The researchers mentioned the vibrissae, the whiskers, as a likely tool for gauging width right at the point of entry. And of course, there's the cat's anatomy.
Right, they don't really have functional collarbones, do they?
Precisely. Their shoulder blades aren't rigidly attached, which gives them that incredible ability to compress their shoulders and rib cage to get through narrow spots. So maybe they just know they're good at squeezing that way.
Okay, so for narrow, it's kind of give it a go, see if I fit. But what about the other scenario? The openings that stayed wide but got shorter and shorter.
Now that's where things changed quite dramatically.
How so?
When those openings got shorter, the cats did start showing clear hesitation.
Before they went in.
Both before they even approached properly, and also sometimes while they were trying to pass through the really short ones, they'd pause, maybe look around more.
And did all cats react the same?
Well, what was really telling was that the taller cats, just naturally bigger cats, were significantly more likely to hesitate and also more likely to look for an alternative solution, like trying to jump over the panel when faced with those uncomfortably short openings.
Whoa. Okay, so when the ceiling got low, then they seemed much more aware of their own body size, especially their height, and whether they'd actually fit comfortably. They were less likely to just blindly try and squeeze.
That's the key finding. It suggests they do possess body size awareness, particularly concerning their vertical dimension. It's like they have a better sense of how tall am I than how wide am I. Maybe because width is more compressible for them.
And the study mentioned dogs, right? How do they compare?
Yeah, they contrast this with what's generally observed in dogs. Other research suggests dogs tend to hesitate before even trying to go through openings that are clearly too small for their shoulders or body width.
So dogs make more of an upfront decision based on size.
It seems that way, yes. Suggesting perhaps a more pronounced or maybe just different kind of body size awareness, especially regarding width in dogs, compared to what they saw in these cats with narrow openings.
Why would there be such a difference? Cats and dogs, they both navigate complex spaces.
The researchers float a few interesting possibilities. It could tie back to their predatory styles.
How?
Well, cats are often ambush predators. They rely on stealth, slow, careful movements, agility, using those whiskers up close. Their whole anatomy is geared towards squeezing into tight spots to hide or follow prey.
Right.
Dogs, especially many breeds, are more often pursuit predators, moving faster over open ground. For them, misjudging an opening and colliding at speed or getting stuck could be more dangerous or costly.
So maybe dogs evolved a more cautious, measure twice, cut once approach to obstacles.
Possibly. While cats, confident in their flexibility and maybe using whiskers for the final check, are more willing to try narrow gaps, but are more wary of low ones where flexibility doesn't help as much and they might feel more vulnerable.
So to sum up that study, for tall but narrow gaps, cats seem to use a bit of trial and error, maybe helped by whiskers and experience. But for short gaps, they do seem to rely more on an awareness of their body height, possibly due to anatomical limits and maybe predator avoidance instincts, like not wanting to be forced into a low, vulnerable posture.
That's a really good summary of their interpretation, yeah. They suggest body size awareness kicks in more strongly for those short openings.
It's fascinating. Did the study have any limitations we should know about?
Well, they do mention one practical thing. Because they tested the cats in their owners' homes, which is great for making the cats comfortable, it meant they couldn't perfectly standardize the starting distance for every trial.
Ah, okay.
So they couldn't precisely analyze the approach latency, like how long it took the cat to decide to walk towards the narrow openings. But they could still clearly observe the hesitation or lack thereof right near the opening itself.
Gotcha. Still sounds like really valuable data on how cats perceive these things.
Definitely.
Okay, so let's try and bring these two big ideas together. We have the physics view. Cats can act like liquids, given enough time, because they conform to containers. That's about relaxation time and the Deborah number.
Right. Based on passive material properties over time.
And then we have the biological view. Cats aren't just passive blobs. They actively assess openings, especially low ones, suggesting they do have an awareness of their own body size that influences their choices.
Exactly. Active perception and decision-making. So how do these fit together? They sound almost contradictory at first glance.
Yeah, are they liquid or are they smart about their size?
Well, maybe it's not either. Observe that amazing molding into shapes could be seen as a consequence of their inherent flexibility, their unique anatomy, combined perhaps with a learned understanding through experience of just how much their bodies can deform and squeeze. They know they're good at it for width.
So they might not consciously calculate the exact width needed for a narrow gap beforehand, as the biology study suggests.
Right.
But their physical ability to become liquid-like in that situation allows the trial and error approach to work most of the time. The physics enables the observed behavior.
That seems like a reasonable synthesis. The rheological perspective highlights why they can fit into surprising shapes over time. The biological study shows how they decide whether to try, revealing that this liquidity isn't deployed uniformly. They're more cautious when their actual non-compressible dimensions, like height, are challenged.
So the cats as liquid meme, while funny, actually points to a genuine physical property, their adaptability of form over time, which is a core idea in rheology.
Exactly. It's a great accessible example of concepts like relaxation time and the Deborah number. But the biology reminds us they aren't just passive fluids. They're active agents interacting with their world.
So maybe the best description is the title of that paper, Cats Are Almost Liquid.
I think that captures it pretty well. Liquid-like in their conformability in many situations, but also constrained and guided by their biological awareness of their physical selves.
It's a really neat intersection of physics and biology. It definitely makes you look at your own cat, if you have one, attempting to get into a tiny cardboard box with a bit more scientific appreciation.
Absolutely. And, it sparks other questions too, doesn't it?
Like what?
Well, we talked about stress maybe affecting relaxation time.
Yeah.
Could a cat's level of comfort or trust in its environment influence how quickly or completely it molds into a space?
How interesting. Like, would a super relaxed cat in its favorite safe spot achieve peak liquidity faster than a slightly nervous cat in a new place?
Maybe. The sources we dove into didn't directly test that, but it feels plausible, right? It links back to that idea of the cat's internal state affecting its physical behavior. It's a great thought to ponder.
It really is. A potential follow-up study for someone.
Yeah.
This whole deep dive feels like it's just scratched the surface, really. There's so much more to understand about how cats perceive the world and, well, the physics of everyday stuff around us.
Indeed. There's a whole universe in rheology, and animal cognition is constantly revealing new surprises. Plenty more to explore out there.
Well, thank you for joining me on this deep dive into the surprisingly complex and slightly strange question of whether cats are liquid. It's certainly given me a lot to think about next time I see a cat contemplating a box.
My pleasure. It's been fun flowing through the science with you.